Hey there, curiosity dudes and dudettes. Welcome back to another mind-bending journey with the Curiosity Dude. Today, we're diving deep into the annals of time to explore the 5 mass extinctions that rocked our planet and asking the burning question, are we living in the 6th? From the mysterious Ordovician-Silurian event to the dino-destroying Cretaceous-Paleogene extinction, we'll uncover the causes, the aftermath, and the lasting impact of these monumental events. And most importantly, we'll look at the current signs that some scientists say could indicate we're on the brink of another massive die-off. Spoiler, it's not just about meteors and volcanoes this time. If you're as fascinated by Earth's history and future as we are, hit that like button, subscribe to stay updated on all our latest videos, and don't forget to ring the bell so you never miss a new upload. Your support helps us keep the curiosity alive. Let's jump right in. Don't forget to drop a comment below with your thoughts on whether we're heading towards another mass extinction. Thanks for watching. Human evolution can't be separated from the evolution of the entire biosphere. Our journey has always been intertwined with a variety of other creatures. It's impossible to detach us from the history of all living matter on this planet. Looking back, we see that this living matter didn't develop continuously but in spurts. Stability, and then bam, something changes. Then stability again and bam, another change. In the early 20th century, this was a surprising revelation. Now, with more knowledge, we see that's how it works. Evolution isn't some mystical force or random chance. It's a pattern of randomness or random patterns. Changes in the environment, like sunspots, supernovae, or volcanic eruptions, aren't influenced by living organisms. They just happen. Meanwhile, organisms have random mutations. They either adapt or go extinct. Successful mutations stabilize, and over millions of years, nothing much changes. But this calm stability eventually ends with mass extinctions. And that's the focus today, mass extinctions. They're crucial because they clear ecological niches. And in those emptied niches, new life forms emerge. When something dies out, something new appears. Each extinction drastically reduces biodiversity, followed by an evolutionary boom, creating many new species, while some of the old ones persist. Look, not everyone dies off, right? The basic species stick around, and new ones just keep showing up. And there have been tons of mass extinctions. They happened at the boundary of nearly every geological period. Sometimes it feels like it's all just karma, like, oh, the period ended, boom, everyone's gone. It's like a curse of the period's end, where every time one wraps up, a mass extinction kicks in. But honestly, that's just a glitch in the matrix. It's like saying the wind is blowing because the trees are swaying. Nope. It's not that the period ends with extinction, it's that the explosion of new species after the extinction starts the next period. Geologists and paleontologists mark these periods, eras, epochs, stages, based on the rise of new ecosystems. Mega-extinctions happened even before the Cambrian period. Take one massive wipeout, for example, in the Proterozoic era. Back then, a ton of photosynthetic organisms appeared, hogging up CO2 and water to make organic matter. Their waste product? Oxygen. It started filling up the atmosphere. At first, no one really cared because, hey, no noses around to smell it. But things went south when oxygen started flooding the oceans. At some point, oxygen levels got so high that everything died. See, it was a world full of anaerobes, organisms that hate oxygen. To them, it was a deadly poison, like some toxic chemical weapon. They didn't stand a chance. The ones that survived were the ones that had built-in oxygen shields, hiding out in bacterial films or the lower levels of stromatolites, where they had to deal with some oxygen thanks to their neighbors. At first, they just fought it off, but later, they learned to use it. And so, most of the ecosystem, probably more than 90% of it, died off. But guess what? The underdog species that had been squished under their successful neighbors' feet suddenly found themselves on top. Well, there weren't any horses around yet, but metaphorically, they were riding high. And that whole breathing oxygen thing turned out to be pretty handy. You could pump all that energy into building solid structures, making bigger bodies, even becoming multicellular. Suddenly, you could grow huge, crawl around all day, maybe even dig into some sand. And if you're made of solid materials, you can start digging up stuff buried under the ground layers, which kickstarts the ecosystem's metabolism. When the Precambrian era ended and the Cambrian started, some creatures figured out how to dig vertical burrows, just a couple of centimeters deep, but hey, vertical burrows nonetheless. This started recycling organic matter back into the ecosystem that previously just sat around doing nothing. Boom, Cambrian explosion. The old Vendian fauna was gone, and the new Cambrian fauna took over in style. But between all those periods, Cambrian, Ordovician, Silurian, Devonian, Carboniferous, Permian, you had these mini extinctions too. Sometimes, they even happened within a period. And when it comes to the ancient Paleozoic extinctions, we're still not really sure why. It could have been a lot of things: volcanic eruptions, asteroids, comets. Every time you dig, you find a crater, a volcano, or some meteoric impact that could explain it. But here's the kicker: sometimes there are craters and no extinction happens. Go figure. Sometimes changes came from life itself, like how oxygen breathers ruined the fun for anaerobes. Take the first land plants. When they developed roots, they started breaking up the soil. Before that, the land was just layers of dead material, rainwater, and maybe some slime. But then, these new roots started loosening the soil, and nutrients, nitrogen, phosphorus, etc., started washing into the ocean. Now, organic material on land wasn't much, but it was enough to enrich the ocean with goodies. And if cooling was happening at the same time, that dissolved even more oxygen in the water, leading to a boom in algae growth. These algae would bloom, die off, and then bacteria and fungi, which have always been around, would break them down, using up all the oxygen in the process. And what do you get when there's no more oxygen? A mass die-off in the oceans, not just rivers or lakes, but full-on ocean-sized extinction events. Plus, throw in a supernova or two just to spice things up. Could you even record a supernova flash over 400 million years? Well, probably not, but it's fun to think about. And these ecological changes? Totally possible. We know a lot more about the extinction at the end of the Paleozoic, which was one of the most intense, if not the most intense, extinctions in Earth's history. This was at the end of the Permian period. Now, the Permian period is pretty fascinating. In terms of aquatic fauna and flora, it's classic Paleozoic stuff. But when it comes to land life, it's so different that we could easily just lump it into the Mesozoic era. Seriously, if periods were defined by land critters, the Permian would definitely be the first Mesozoic period, 100%. But climate-wise, it was different because the Mesozoic was the warm era, while the Permian was a cold one, a chilly era. At that time, all the continents had smushed together into one big supercontinent called Pangaea. This messed up ocean currents. Sure, it was warm at the equator, but just a bit farther away, it was freezing and dry. So, a lot of animals had to adapt. Gymnosperms showed up, which were great at surviving dry conditions. We also got the warm-blooded, mammal-like reptiles with actual noses, more complex behaviors, running faster on their legs, and even early versions of different types of teeth, like a prehistoric dental experiment. These guys were almost mammals. They had whiskers, but they were still reptiles, just very fancy ones. And this whole happy setup lived in such strange conditions, but then towards the end of the Permian, everything collapsed, triggering the mega extinction at the close of the Paleozoic. And this wasn't just the end of two periods, this was the end of an entire era, the Paleozoic making way for the Mesozoic. The reasons were complex, as always. Of course, there are the catastrophists, the ones who think it all came down to a big boom because, let's be honest, that's a simpler comic book way of thinking. Something blows up and bam, everyone's dead. Some point to the Siberian traps, or even the emission traps in China, though the Siberian ones are more famous. This is when, in western Siberia, around where the Ural Mountains are now, huge amounts of magma started oozing out of the ground. And we're not talking about a nice, neat volcano where lava just drips down. No, this was massive lava floods covering huge areas. We're talking mountains of magma, stretching for kilometers, maybe even creating the Ural Mountains. It makes sense that something this dramatic, happening over millions, or at least hundreds of thousands, of years, would have completely changed the atmosphere and the chemical composition of the oceans. Now, the real question is, did all of this actually change the world that much? Because, not too far from those Siberian traps, you still find deposits with actual flora and fauna. Some little creatures were crawling and running around. I mean, sure, they weren't hanging out directly in the lava. Nothing survives in lava, obviously, but in nearby deposits, you find things like dicynodonts, those mammal-like reptiles, and other critters scurrying about. So, life was definitely still happening, even right next to these erupting volcanic areas for thousands of years. But there are also purely ecological reasons for these extinctions. For example, at the end of the Paleozoic, during the Permian period, that supercontinent Pangaea started breaking up. It began to split into Gondwana in the south and Laurasia in the north. As the continents drifted apart, new ocean currents formed. And when you've got sunshine heating the water at the equator, those warm waters start moving around, especially towards higher latitudes. Now, we're currently in an ice age, technically in an interglacial period, but still pretty chilly, right? Back then it was the opposite. And while we think warming up is a good thing, yay, summer, everyone's happy, back then, rapid warming was actually a nightmare. The thing is, when it gets too warm, oxygen doesn't dissolve as well in water. This also messes with the levels of carbon dioxide, changes the water's acidity, and for the little guys living in the ocean, this was a major crisis. At the same time, more powerful plants started to show up, like I mentioned earlier, gymnosperms. No flowering plants yet, but gymnosperms were getting pretty advanced, and they had a legit, well-developed root system. Big roots, thick roots, and even some smaller ones thrown in for good measure. Now, if back in the Ordovician or Silurian periods, roots were mostly just fluffing up the soil, since they were tiny and didn't have any serious structure, by the Permian, these new roots were actually locking the soil in place, stopping it from washing away, and preventing all those good minerals from flowing into the ocean. So, in the oceans, oxygen levels started dropping, acidity went up, and the amount of nitrogen and phosphorus was getting lower. Basically, life in the ocean was starting to suck pretty hard. And to make things worse, along came these annoying mayfly larvae. And not just mayflies, oh no, stoneflies, caddisflies, all sorts of little critters that were spending part of their life cycle in the water. The larvae would hatch there, grow up, gobbling up all that tasty nitrogen and phosphorus, then crawl out onto a plant, sprout wings, and fly off. Once airborne, they'd lay some eggs back in the water and then go off somewhere on dry land to die. Now, you'd think, one mayfly? Who cares, right? I even tried to find out how much a mayfly weighs in some literature, and I couldn't find anything. Maybe nobody ever bothered to weigh one because they're just so tiny. Or maybe I missed it. Either way, it doesn't matter. The point is, sure, one mayfly, no big deal. But when this kind of thing happens for millions of years and there are swarms of them, yeah, that starts to add up. So, For example, in modern times, we've seen a pretty wild event where, after a mass mayfly hatch, they end up covering the ground in a 1-meter thick layer. Yeah, that's from just one day of mayflies, who only live for, like, a day. And when you get a whole meter-thick pile of them, that's not just a nuisance, that's tons of mayflies, literally. And that's happening today, where we actually have creatures around to eat them. Sure, a lot of them take off in some rainy evening when no one's out to snack on them, but still, they mostly get eaten. Now imagine back then, when things were way simpler, and this sort of mass hatching was happening for millions of years. You've got tons of mayflies sucking up all the useful minerals from water, flying off, and basically robbing the ecosystem. And on top of that, gymnosperm roots were holding everything in place, locking down any nutrients that should have been washing into the oceans. Add to that temperature changes, acidity changes, and just about every other environmental shift you can think of. Oh, and don't forget those annoying Siberian traps that were erupting nonstop for millions of years, spewing lava and causing all kinds of chaos. So, it's no wonder things got bad, really bad. In fact, even without those Siberian traps, it was already shaping up to be a disaster. And then, of course, there was the warming, which no one was prepared for. The result? One of the worst mass extinctions ever. Nothing like it had happened before, and nothing that bad has happened since. By the end of the Permian, the oceans had lost up to 96% of species. That's basically everything gone, and the 4% that survived? That's practically within a margin of error. In society, around 4% of people are thought to have schizophrenia, but you don't really see them, right? Well, it's kind of like that. Those 4% of species just barely made it through. Even on land, things weren't much better. Around 75% of species vanished. So, yeah, 3 out of 4 species gone just like that. Interestingly, while species extinction was massive, it wasn't quite as bad at the family level. About half of all families disappeared. So, what that means is half the families of species were wiped out, while in the surviving families, maybe just one species hung on by a thread. Where there used to be tons of species in each family, now there was just one lonely survivor per family. And then, moving into the Triassic period, something wild happened. Life bounced back with a huge diversity of species. It's surprising, right? On the one hand, almost everything had died, but on the other, the seeds of future diversity were still there. That's why the Triassic was such an amazing time. There wasn't any single dominant group lording over everyone. Unlike later, when dinosaurs took over or now with humans calling the shots, the Triassic was like nature's sandbox, full of all kinds of different creatures figuring things out. No one species ruled the roost. In the Triassic, you had all sorts of newcomers: early crocodiles, dinosaurs, pterosaurs, mammals, and maybe even the first birds, though that's still up for debate. There's a very questionable first bird, but hey, something bird-like was flapping around. Plus, there were early versions of modern sharks, new fish species, and who knows what else. It was basically a big evolutionary playground. Of course, the fun didn't last forever. By the end of the Triassic, another mass extinction hit. And looking at it by percentages, you could almost call the Triassic its own era, sandwiched between mass extinctions. The end Permian extinction was the big one, but the Triassic extinction wasn't far behind. About 3/4 of species were wiped out again, especially in the oceans, though land animals fared a bit better, with around half disappearing. Still, the end Triassic extinction was actually more significant than the one that took out the dinosaurs at the end of the Cretaceous. Yet for some reason, we don't call the end of the Triassic a boundary event like the one at the end of the Cretaceous. No logic here. Don't try to find it, because these periods and eras were mostly made up in the 19th century and not based on solid math or statistics of extinction. It was more like, oh, I found some new rock layers, I guess it's a new period now. That's how it went back then. Later on, people tried to make sense of it all, but honestly, it's still a bit arbitrary. Anyway, the Triassic ended with a bang. There are lots of ideas about why. Some say volcanoes erupted, others suggest meteor impacts, or even huge craters popping up. But the main culprit seems to be, once again, changes in ecosystems. Over time, ecosystems had built up internal contradictions and weaknesses, making the whole system unstable. What's funny is that while global temperatures didn't change all that much, local climates definitely did. Towards the end of the Triassic, there were swings between warming and cooling. So, depending on which theory you read, you'll find some people saying the extinction was caused by global cooling, while others say it was due to warming. It's like, wait, what? How can it be both? Turns out it was both. Some areas got hotter, others got colder. CO2 levels spiked in some places and dropped in others. It was a real mess of contradictions. Actually, it all makes perfect sense if you think about it. The real killer is when the environment is stuck on these extreme mood swings. First it's warmer, then colder, then warm again, then oxygen levels spike, then drop, then CO2 surges, then it's gone. It's like nature's worst roller coaster, and that's exactly what led to mass extinction events. The last of these mega extinctions hit at the end of the Cretaceous period. You've probably heard all about the meteor theory, Chicxulub hitting the Gulf of Mexico, Shiva impacting the Indian Ocean. Now, there's even another crater they found in the Atlantic. It's highly likely these were all pieces of the same giant space rock that shattered before hitting Earth, with different chunks falling as the planet turned. There's even a theory that these massive impacts may have literally cracked the Earth's crust, leading to enormous lava flows called the Deccan Traps in India, giant mountains of lava as tall as skyscrapers. Yet, despite all this destruction, we still find traces of life near these impact zones. Even close to the Chicxulub crater, there's evidence that something was burrowing around just 4 years after the meteor hit. Nature bounces back, right? But maybe the real story was the slow, steady changes in ecosystems, the rise of flowering plants, shifts in water acidity due to increased silica runoff, and changes in tiny ocean life forms. The one-celled creatures that used to build the famous chalk deposits of the Cretaceous were replaced by others making shells out of silica. On land, the big reptiles were locked in a fierce competition, and in the oceans too. The biggest dinosaurs and marine reptiles dominated everything smaller. This constant pressure lowered overall biodiversity. There just wasn't room for a lot of species to thrive when one giant dino could outcompete every smaller and mid-sized species throughout its life cycle. A dinosaur starts small, competes with the little guys, then grows bigger and competes with the mid-sized ones, and then finally becomes a 30-meter-long monster competing with other giants. No wonder biodiversity took a hit. So while we often think of the mass extinction at the end of the Cretaceous as sudden, it wasn't. The decline in dinosaur diversity was a slow burn over tens of millions of years. Sure, the meteor or volcanic eruptions might have been the final nail in the coffin, but the downward trend had been happening for ages, due to competition, ecosystem shifts, and other environmental changes like the rise of flowering plants. In the end, it wasn't just one disaster, but a perfect storm of catastrophes spread out over a very long time that sealed the fate of the dinosaurs. So, really big changes were happening in the middle of the Mesozoic era. If we're talking about plants and insects, we should be looking at boundaries, actually. At the end, the reptiles went extinct, and that's a big deal for us, mostly because everyone loves dinosaurs, until they have to face one in real life, of course. But we're long past that now. As we move into the Cenozoic era, things are becoming clearer, especially concerning the antics of mammals. But here's the sad part. We're currently living in a mass extinction that we ourselves have caused. Even without any mega changes to the climate, we're just too active of a species. We consume a lot, produce a ton of waste, and compete with everything. We're up against bacteria, fungi, cows, bears, and fish in the ocean. Basically, anything that's alive is competing for resources. The difference is, we do it with an unparalleled efficiency. We're so effective at destroying habitats that the rate of current extinction is actually much higher than what happened at the end of the Mesozoic. So, in a few million years, this current time might be viewed as the moment of the great monumental extinction, marking the boundary of a new geological period. There's even talk of officially recognizing a new period called the Anthropocene, but that feels a bit fake. The real Anthropocene will be when biodiversity starts to bounce back after this decline. Right now, we're just shrinking that diversity, and who knows what that future resurgence will look like. It could be sparked by us if we make it through this crisis and actually start fostering biodiversity ourselves. But for that to happen, we need some serious smarts. So, pump up those brain cells. Don't contribute to this global extinction. Don't let yourself go extinct either. Leave comments, share what you know about past mass extinctions, and if you think I've got it all wrong, give me a thumbs down. But if you're on board, hit that like button and subscribe for more interesting stuff ahead. We've got a lot of exciting content coming your way.